Hi, and thank you for joining us for the Managing Bandwidth and Commits with Noction Intelligent Routing Platform webinar. We hope we will give you plenty of valuable information to take away with you today. As you probably know, the Internet is a huge mesh of networks which are interconnected by routers running BGP. Typically, routers have multiple paths to the same destination. The Border Gateway Protocol calculates the best path by applying a complex algorithm. BGP is a fundamental technology for fault tolerance on the Internet, and it is accomplished by choosing network path based on the number of autonomous systems that the traffic must traverse before it reaches its destination. However, BGP does not take into account important factors of network performance. Even if multi-homing does provide some redundancy, multiple network outages have shown that multi-homing alone is not the solution for risk diversity and business continuity. When major blackouts or even congestions happen, multi-homing gives a fallback link for the first mile connection, rather than providing a way to route around the Internet middle mile issues. Noction IRP adds intelligence to multi-home routing decisions. It leverages the company's existing infrastructure to deliver substantial network performance improvements, optimizing the existing Internet connectivity and significantly reduces the cost of operating the network. Commit control allows the IRP to keep the commit levels for each provider at a preconfigured level. It includes bandwidth control algorithms for each provider, as well as active traffic rerouting, which is triggered when bandwidth for a specific provider is in danger of reaching a preconfigured limit. Commit control also includes passive load adjustments inside of each provider group. A parameter called precedence is used to set the traffic unloading priorities, depending on the configured bandwidth cost, link capacity, router load, and provider's throughput. The higher the precedence, the lower the probability for the traffic to be sent to this provider when its preconfigured 95th percentile usage is higher. The platform will route excessive bandwidth to providers when their current load is less than their 95th percentile. If all providers are overloaded, traffic is rerouted to the provider with the smallest precedence. Usually this provider has either the highest available bandwidth throughput or the lowest cost, but clients will often take into account router load when configuring the system. The Intelligent Routing Platform Commit Control algorithm provides an extensive instrument in controlling the bandwidth usage of a link while keeping the performance at acceptable levels. Before making a routing decision, it considers a number of factors to ensure traffic patterns fit the configured network preferences. The first thing it will consider is the current bandwidth usage for each provider link. This is accomplished by reading SNMP counters from interfaces where uplinks are connected. The data is stored in local databases and is used for a 95th percentile mathematical calculation. Once data is ready, IRP will check for any configured routing policies and compare the performance metrics for each provider. The next step would be checking the provider's precedence setting. We have previously described how precedence is used in IRP, but it can be anything from cost, link saturation points, or even router load. Besides this, IRP will estimate the impact of making a routing decision for a certain prefix by checking particular prefix stats. This is usually accomplished by reading flow data. This helps balancing traffic evenly across available links without overloading other links. As soon as the above steps are completed, IRP will make a routing decision. IRP is continuously checking past decisions and looking for new options. The IRP commit control algorithm workflow is represented in the following diagram. Here we can see the steps described in the context of multiple prefixes that are triggered and rerouted by our commit adjusting algorithm. As you can see, in case of a provider overload, IRP will build a list of prefixes eligible for rerouting based on commit reasons for each of the overloaded providers and apply the same steps for each of them. I would like to note that IRP checks performance for potential reroutes. Before making a routing decision, IRP will verify if the performance through the new candidate provider is not worse than through the overcommitted link, or in case, if it is worse, that worsening is within acceptable levels, all of which can be customized. Worsening the performance is only allowed in latency matters, and it can be configured in the core settings of IRP. Once all prefixes are prepared for the first peer and have been verified, they are then rerouted. If applicable, IRP will proceed with the list for the second provider, and so on. As soon as all overloaded provider prefixes will be validated and rerouted, IRP will start over with the first peer again to make sure the performed improvements did their job, and continue to do so. Once all prefixes are prepared for the first peer and have been verified, they are then rerouted. If applicable, IRP will proceed with the list for the second provider, and so on. As soon as all overloaded provider prefixes will be validated and rerouted, IRP will start over with the first peer again to make sure that performed improvements did their job and continue to do so, and that links were unloaded correctly. It will also see if there are new prefixes overloading the links, either now or in the near future. Now that we know how commit control works, let's see what IRP requires in order to maintain link load at required levels. IRP needs to read interfaces counters by SNMP. The first obvious requirement is to configure the SNMP read-only access on the border routers. Next, IRP needs to know your contracted commit levels for each link. IRP can also benefit from knowing the day of the month your provider bills you, along with the precedence level in order to protect some providers more than others. Besides basic parameters, we can fine-tune commit control aggressiveness with regards to previous overloads and control at what stage IRP begins to take action. This way, IRP will predict overloads and proactively reroute traffic, even before the link reaches its commit limits. In many cases, multiple links for the same provider exist. In this case, IRP can group these providers together, and a limit can be set on the group. In this scenario, IRP will take action only when the sum of the bandwidth usage on all providers in the group exceeds the sum of bandwidth limits for the same group of providers. The rationale of this feature is that overusages on one link are compensated by overusages on another provider link, and there is no need to take any actions since the overall commitments made to the ISP have not been exceeded. Another possible scenario is the possibility to evenly balance the traffic over multiple providers or multiple links with the same provider. For example, a specific network having an average bandwidth usage of 6 GB per second has two separate ISPs. The network operator wants, for performance or cost reasons, to evenly push 3 GB per second over each provider. In this case, both upstreams are grouped together and IRP will actively route traffic for an even traffic distribution. Now let's take a closer look at the most important IRP commit control algorithm parameters. The first thing to configure when considering commit control is the physical interface limit load. Here we can recommend setting the value at 90% of the real link. For example, if you have a 10 GB interface, we need to set limit load to 9,000 MB per second. Once done, IRP will be able to avoid overloading a physical interface. Next, we set the agreed commit levels with ISPs and provider billing day value from 1 to 30. In case you want a certain provider to use committed interface rate instead of 95th percentile, we can set the billing day to -1. Now that we have commit levels in place, we need to set the traffic unloading priority. This is accomplished by using the precedence field. The higher the precedence, the lower the probability for the traffic to be sent to a provider when its preconfigured 95th percentile usage is higher. The platform will reroute excessive bandwidth to providers whose current load is less than their 95th percentile. If all providers are overloaded, traffic is rerouted to the provider with the smallest precedence. As some providers may have non-standard traffic billing policies, the centile value can be also configured to something other than 95th. Flow agent specifies a collection of matching pairs for the flow source and the physical interface that carries traffic. If configured, commit control will be able to react faster to commit overloads and reroute traffic more efficiently. In order to configure commit groups, we need to set the same precedence value for 2 or more providers. Once done, IRP will automatically group them together and start unloading the traffic as required. Also, within a commit group, you can enable or disable separate costs and performance improvements. If enabled, IRP will perform reroutes from and to peers within the same group if cost or performance is better. On the other hand, you have the possibility to enable load balancing for peers in a commit group, and you can set the parameter max deviation in percentage. Last but not least, IRP will consider candidates when latency degradation is not exceeding this limit. Of course, the candidate with the least latency degradation, or even with better latency, will be chosen as an improvement. When IRP detects that an existing commit control improvement has alternatives with latencies better than the specified value, it will replace it with a new performance improvement. Overusage of the alternative route will be avoided. Most of the mentioned parameters can be configured at the commit control configuration section, as it is in the example. Instead of jumping through each peer configuration, our provider's overall table offers a summary of the individual peer configuration, the commit and load balancing groups, costs, 95th calculation mode, as well as precedence of each peer. Also, here we can check monthly 95th bandwidth usage and current bandwidth usage for each provider. On the commit control configuration page, we can group peers in commit groups or load balancing groups. While you'll be unable to see configured groups of peers in individual provider configuration page, here we can already see providers being grouped by commit or by load balancing criteria. Here we have a screenshot of the IRP current improvements report with focus on commit reroutes. The report indicates the timestamp when the improvement was done, old and new provider names, the cause, age, and details of a given reroute. For commit control improvements, IRP will also report back the prefix bandwidth user statistics, which were calculated in order to make an estimation of any given reroute impact on the total bandwidth usage for all and new provider links. Here we can also see the type of improvement, global or local, when using multiple routing domains feature, and we have the possibility to remove any of the performed improvements. Now let's move further and see how easy it is to configure commit control and start unloading traffic from our peers.
Let's go to the IRP configuration section, Providers and Peers. We could jump straight to commit control configuration page and start right away, but since we want to have a very fast commit control algorithm, we will configure the flow agents. Agents are configured in the following format: flow source IP address, which is usually the router sourcing flow IP address, / interface IF index. For our case, we've already collected this information. If you are unsure, you can always go to SNMP configuration and IRP will give you a hint on the provider interface IF index. For Cogent provider, we'll type in the source IP address manually, with IF index being 614. Let's do the same for other peers, such as for Zayo, with the IF index being 678. For BBOI, we have IF index 694. And for Telia, it is 716. Then click Submit. Now we are ready to set required commit-related parameters in the Commit Control Peer Configuration tab. First, we set provider 95th percentile value as per our agreement with ISPs. For Cogent, it is 600 megabytes per second. For Zayo, it is 2,800 megabytes per second. BBOI, 1,700 megabytes per second. And 2,000 megabytes per second for Telia. As we want IRP to use committed interface rate instead of 95th percentile, we will set the billing day to -1 for all peers. This is done for demonstration purposes only, and in real case scenarios, we could set this to an actual day of the month instead of -1. The next must-have parameter is the precedence value. Based on our agreement with the peers and cost per megabyte per second of traffic burst, we have defined some internal preferences over which provider we want to reroute traffic in case when all links are overloaded. Because we don't want to black hole any traffic, we will reroute overloading traffic over peers with lower burstable costs, which in our case is Telia. Now, let's click the Submit button. Now we're going to enable commit control for each peer. Besides the configured parameters, we see another ones, with default values in place. Depending on your agreement with ISPs and your preference, all of them can be adjusted. With configuration adjustments completed, let's turn the commit control for each of the providers. Then we click the Submit button. After that, we enable the commit control globally. This can be done by switching to commit control configuration page and turning the switch position on. Also, let's expand advanced setting and turn on the React on IRP flow dstats switch. This parameter will tell IRP to make use of previously configured flow agents for providers and improve commit control rerouting time for commit improvements. Within a few minutes, if any of the peers are being overloaded, IRP will start rerouting traffic. Let's go to IRP Current Improvements report and see how this works out for us. Perfect, we see the improvements being performed. The most recent one rerouted traffic from Zayo to Telia. We can also see the estimated amount of traffic carried by prefix, as well as the source and destination providers and their loads. As you were able to see during this configuration showcase, one does not require advanced knowledge of router operating system to reroute overloading traffic. Since it is done via GUI interface, IRP excludes the possibility of black holes caused by human error. Further on, once the configuration is completed, the intelligent routing platform will automatically check the link statuses and if an action is required, so you don't have to monitor your ISP link 24/7 in order to avoid bandwidth burst that can eat a pretty large part of a company's budget.
Now that we've shown how the intelligent routing platform commit control works and how it is configured, let's take a look at the inbound commit control algorithm. Internally, the measurements and decision-making mechanisms are the same as for the outbound commit control and can be used in combination with outbound commit or completely separate. This would usually depend on the agreement with the ISPs, specifically how they calculate the 95th percentile usage, outbound plus inbound or outbound and inbound separately. Because inbound traffic manipulation is more challenging than outbound, IRP will be using well-known mechanisms to reroute inbound traffic via available links such as AS path prepends or well-known provider-specific communities. In case provider is allowing other BGP attributes such as local preference, multi-exit discriminator, etc., Noction deployment team will be more than happy to integrate those with the IRP system. Since inbound traffic reroutes may have a noticeable impact on the network, IRP offers the possibility to do semi-automatic inbound improvements. Basically, IRP will analyze the bandwidth usage per each prefix and provider interface and propose some appends for a certain link, increase or decrease the number of appends. At this point, you can review proposed appends and commit or discard proposed changes. Once all inbound tests are passed successfully and IRP gained your trust, it can be enabled in a fully automatic mode. Once it is enabled, the fully automatic mode, IRP inbound commit control will make use of Notion's proprietary algorithms in order to consider internal nature of inbound traffic rerouting specifics. This is everything that Noction planned for this webinar. Shall you have any further questions on how IRP will help reduce your company's expenses on networking? Please visit our website at www.noction.com or our social media accounts listed on the slide. Thank you for your time, and we're looking forward to hearing from you soon.